Okay. So in the previous class, we learnt a statement of Gibbs phrase rule, which is F is equal to C minus P plus 2, where F is the number of degrees of freedom, C number of components, P number of phases, and two additional variables of temperature and pressure. That's fine. And in fact, we also learned the meanings of these terms F, C, P, and 2, as well as in a given system, how to identify the number of phases, the number of components, and the number of degrees of freedom. In fact, uh, you cannot identify number of degrees of freedom in a given system directly. That is where the usefulness of Gibbs phase rule is. You can identify the number of phases and you can identify the number of components. If you know both of them, applying the formula, you can count the number of degrees of freedom. Okay, but now today we are going to derive this Gibbs phase rule. In fact, it's one of important derivations in thermodynamics, Gibbs phase rule. Before that, we will have a closer look at our system. So, in the first diagram there, you see I have taken a compound I. Fine. So, instead of telling it a compound, I will tell a component, because in our previous class we saw the difference between compound and component. Now, in our derivations, we use the term components, not compound. So, the component I as distributed between two phases, A and B. But there can be systems with more than two phases, phase C, phase D, and it can't go on like that. Now our component I, okay, component I. See, when it distributes between two phases A and B, it is a simplest of the case, is it not? I think this will remind you of Nernst distribution law, like your solute iodine distributing between phase water and phase CCl4, is it not, or chloroform? Therefore, in a binary heterogeneous system like that example, it's easy. But now what you have to do is you have to just extend your imagination and add more phases to this equilibrium. It is not just one phase. There is a second phase, there is a third phase, and go on till n phases. Okay. And our component I is now distributing not between two phases, in the simplest of the case like we were talking before, is now distributing amongst all the available phases n. Okay, that is what I have put in a tabular column here. I have just put in a tabular column here. How many phases are there in this equilibrium, in this system? How many phases are there? There are n number of phases, Pn, P1, P2, P3, Pn, n number of phases. And how many components are there? Of course, again, the simplest of the case is having one component 1, which is distributing amongst n phases. But there can be systems with more components. Therefore, let there be C2. Then what happens now? Component C1 distributes between P1, P2, P3 and goes on till Pn. C2, of course, more than distributing itself, you can rather use the term exist in. So component 2 exists in phase 2, phase 1, phase 2, phase 3 and till phase n. Similarly, there are n components. So now the table becomes spread out, is it not? You have n phases and you have n components. To this system, using this system, we are going to derive Gibbs phase rule. Okay. Yeah. Fine. So now that is what I told. Let us assume an heterogeneous system consisting of n number of phases and n number of components. And let us again assume there is no chemical reaction as the components move from one phase to another. Okay, this is an assumption for the derivation of Gibbs phase rule now. But in many systems, as the temperature and pressure is changed, there can be a chemical reaction between the components within different phases and give rise to new component. Okay, that we will not consider for the time being sake. Okay, let us assume there is no chemical reaction as the temperature and pressure is varied, or as the components transfer transported through different phases, there is no chemical reaction. Okay. Now, when this system is in equilibrium, how many parameters do we require to describe this system? Always, as always, with any thermodynamic system, what are the variables required to specify the system? Temperature, pressure, and the composition of each phase. Fine. Okay. Now, let's calculate the number of variables. The total number of variables required to specify the state of system is pressure, which is same for all phases, temperature, which is again same for all phases. So, two variables, we take it very straightforward. So, two variables we require to define the system. But what about the composition of each phase? Is it same? Is it same, identical? That means as the given component distributed identically in all the given phases? May not be. Therefore, now we have to find how many concentration terms or composition terms do we require to completely define the system. Okay. Now, if there are C components in one phase, let us assume like this. In one phase, there are C components. Okay. Now, how many compositions you have to specify to give the complete picture of that phase? Okay. Please note the difference between components and composition. Components, here you may take it now as equal to, for our understanding sake, as a chemical compound. What about composition? What is the percentage of different chemical compounds in one phase? This is all. That's all. Okay. Now, for example, I have two compounds in the phase. If I tell the composition of the phase is as follows. Two compounds A, B. A is 40%. Do you have to tell B is 60%? No, because there are only two components and a single phase. So all that you have to specify is the composition of one component, that is A, 40%. The remaining composition is automatically fixed. Now there are three components in that phase. Let us assume. Then and I tell you that it is like this. The composition is like this. What is that? A 20%, B 30%. And do you have to tell C now? No, because automatically it will be fixed as 50%. Is it not? So in any given phase, if there are C number of components, how many compositions you have to specify? If there are two components, one composition. If there are three components, two composition. And if there are four components, three compositions. If there are n C components, C minus one compositions. Is it not? In a single phase. But now we have n phases in our system. Therefore, the total compositions you require to specify, that is P into C minus 1. So that is the total number of compositions you have to write down to completely describe the system along with temperature and pressure. So if I tell how many if I ask you how many thermodynamic variables have to be specified for an heterogeneous system, you straight away tell P into C minus 1 plus 2. Is it not? Plus 2. One comes from temperature, the other comes from pressure. What is P into C minus 1? It is the total number of compositions you have to specify to define the compositions of all phases in the given equilibrium. Is it okay? So now this is an important conclusion. What is that? Total number of variables required to be specified to describe the system completely is P into C minus 1 plus 2. Let us label this as equation 1. Okay. Now, but in the phase rule, we are not going to use, for example, the total number of variables. We are rather using number of degrees of freedom. Okay. What is the definition of number of degrees of freedom? Number of degrees of freedom is nothing but again a thermodynamic variable, but which can be specified independently. Okay, that means the number of degrees of freedom F cannot be more than the number of thermodynamic variables. Okay, this we can say very straightforward, right? Number of degrees of freedom cannot be more than number of thermodynamic variables, but it can be lesser than that. How much lesser? That is what we are going to see now. Okay, now how much lesser? For that, we have to specify certain number of variables only, and other variables will be automatically fixed due to the considerations of the equilibrium condition. Okay, now those variables which are automatically fixed due to the consideration of equilibrium condition, you subtract from the total number of variables. That will be the number of degrees of freedom. Simple. Okay, therefore always F is equal to or lesser than the total number of thermodynamic variables. So F is equal or lesser than V. What is V? Total number of thermodynamic variables. Now how much lesser? That is what our question is, right? It will be lesser by the factor of number of equilibrium reactions inside the system. Okay, so now let us calculate how many number of equilibrium reactions are there for the given system. Okay, fine. So let us calculate E. Fine. Now for this we have to use a concept called chemical potential. Okay, so don't worry too much about the meaning of chemical potential. Chemical potential, you can roughly equate it as your Gibbs free energy G per mole. Okay, but don't worry, the details is not required here. All that you should know is only this much. Now, for example, in an equilibrium reaction, delta G doesn't change, right? Delta G is 0. The change in free energy is 0 for an equilibrium reaction. Or at equilibrium, the change in free energy is 0. Delta G is 0. Similarly, at equilibrium, change in chemical potential is also 0. Okay, and chemical potential is represented by mu. Okay, so for the given component 1, its chemical potential in phase 1 is equal to its chemical potential in phase 2 is equal to its chemical potential in phase 3. See, go on till n phases. Okay, this is the equilibrium condition. It is fixed by the condition of equilibrium. If there is no equilibrium and there is a dynamic movement of the components, or there is a chemical reaction which has not reached equilibrium yet, the chemical potential keeps changing during the reaction or during the phase transition. The chemical potential keeps changing. Once the phase transitions have attained equilibrium, then there is no more change in the chemical potential. At this equilibrium condition, the Gibbs phase rule is applied. Please remember, Gibbs phase rule is applied at an equilibrium condition when the equilibrium is attained between different phases. Only that at that point, Gibbs phase rule is applied. Therefore, the change in chemical potential is 0. So for component 1, you can write this equation. Similarly, for component 2, you can write mu2 P1, go on till mu2 Pn. If there are C components, what will your equation becomes? Chemical potential in phase 1 of component sigma C I, all considered together for C component. For each component, the number of equilibria for P phases. For each component, the number of equilibria for P phases is P minus 1. Okay. For C component, the number of equilibria for P phases is equal to C into P minus 1. Okay. So I hope you understood the meaning of this statement. For each component, the number of equilibria for P phases is equal to P minus 1. Okay. If I want to explain this, you look at this picture again, the table which I have given. Just go back. Okay, fine. Now you see. Now for the given component C1, there is an equilibrium between P2, P1, P3, P2. Now let us think there are only 3 phases. How many equilibrium reactions are there? between P2, P1, between P3, P2. Okay, so there are two equilibrium reactions. So if there are P number of phases, how many total number of equilibrium are there? P minus 1 equilibria. P minus 1 equilibria. Similarly, that is what the meaning of this statement is. Okay, P minus 1 equilibria. For one phase, how many of for one components, how many total components have we have taken? C number of components we have taken. So how many total number of equilibria are there in our system? C into P minus 1. C into P minus 1. Okay, let us take this as equation number 2. What is the relationship between relationship of F with respect to thermodynamic variables? The F is equal to number of degrees of freedom and number of equilibrium reactions is this. F is equal to number of thermodynamic variables minus number of equilibrium reactions. What is the value of number of thermodynamic variables? We have calculated here, right? P into C minus 1 plus 2. What is the number of equilibrium reactions now? That is what we have calculated here. Total number of equilibrium reactions involved is equal to C into P minus 1. So now you calculate, you substitute these values and calculate the number of degrees of freedom. F is equal to equation 1 minus equation 2. Equation 1 is equal to P into C minus 1 plus 2 minus of C into P minus 1. So you expand this, F is equal to Cp minus P plus 2 minus Cp plus C. You cancel the like terms and end up with the final equation. F is equal to C minus plus P plus 2. F is equal to C minus P plus 2. This is nothing but the equation of Gibbs phase rule. Okay, so this is a very important derivation, and this derivation doesn't require rigorous mathematics. Rather, it requires more understanding of chemistry and adaptation of this chemistry in a logical way. So the derivation is more based on logic, is it not? Chemical logic, if I have to put it. Of course, in logic, there is no difference between chemical logic, physical logic, biological logic. Logic is logic. If you are a logical person, you will apply that logic to your entire in all circumstances of your entire life, not only for chemistry, mathematics, and your everyday life, for your bank transactions. Not like logic is logic. But anyways, I'm just telling. Let us apply that chemical logic to our derivation and derive the Gibbs phase rule. Okay, so as I mentioned, this is an important derivation, and you know, if I have to make you more serious, this is one of the favorite questions for your exam setting. Yeah, derive Gibbs phase rule, and it's easier one, in fact, compared to many other thermodynamic derivations. It's an easier one. Okay, fine. So that is regarding Gibbs phase rule. Now we are going to move on to one important aspect of our chapter. Phase rule is phase diagrams. What is a phase diagram? As with any diagram, it is a representation, pictorial representation, or a graphical representation of what and what? Of the conditions, pressure and temperature under which various phases can exist. And transformation from one phase to another phase of the given component can take place. That is what a phase diagram is. I'm going to show you a phase diagram, only then it will be clear to you. The phase diagrams are classified into or the phase diagrams we study in your syllabus are classified like this: phase diagram for one component system and phase diagram for two component systems. The best example for an one component system is our water system, is it not? Because in water vapor, in liquid water, and in solid, there are only one component, that is water. Okay, fine. Now okay, fine. Now component for a two component system, the components which react to form compound as you vary the temperature and pressure, components which do not react even if you vary the temperature and pressure. The example for that is lead silver system, and the example for this again is bifurcated into two things: system having congruent melting point, zinc magnesium system; system having incongruent melting point, sodium potassium system. Now let us start the study of phase diagram with the simplest of the system, that is water system. Okay, fine. The diagram looks at the first look a bit complicated, But if you dissect it out into different parts of the diagram, it is easier to understand. But first of all, let me tell, whenever I talk about phase diagram of water system, I should tell it is phase diagram of water system. Do not use do not use it as phase diagram of water. Okay, water is different and water system is different. Okay, so this is phase diagram of water. Now, how to study the phase diagram of water? Basically, if you leave out all these dotted lines, which we have taken for our reference, you just get only three main curves: OB, OC, and OA. Okay, and these three curves, we call them as stable curves. There is one more curve, OA dash, which is called a metastable curve. We will understand this later. What is a metastable curve? Okay, fine. Now, let us take up each curve and study them separately. Now, what is this curve OB? Curve OB. Okay, this curve OB is nothing but the vaporization curve of water and water vapor. And mind you, when I write a curve like this, the face above this curve is water. The face below this curve is water vapor. Okay. Now let us start our understanding at two conditions of temperature and pressure. What is the two condition? 1 atmospheric pressure and 100 degrees Celsius temperature. At 100 degrees Celsius temperature and 1 atmospheric pressure, how many phases are there? You tell me. Two phases, right? Because that's the boiling point of water. There is liquid, there is also water. Okay. Now, as you, for example, you keep this 1 atmosphere constant, increase the temperature to 110 degrees Celsius. Where is that 110?
1 minute, sir.
You just have to go like this.
Sir.
Increase the temperature to 110 degrees Celsius. Okay, increase the temperature to 110 degrees Celsius. Then 110 degrees Celsius at 1 atmosphere. It comes here, right? At this point. What is the only phase you have? Is water vapor. You don't have water. At the same 1 atmospheric pressure, you decrease the temperature to 90 degrees Celsius. You will get a point here. Is it not 90 degrees Celsius? What is the phase you have? Water. Because the area enclosed between these curves is only water. The area enclosed between these curves is only water vapor. So all that what you have to do is at a different temperature and pressure, you have to see which phase exists. And just keep note downing that phase here on a graph. That will give you phase diagram basically. So that curve OB is nothing but the vaporization curve of water and water. Vaporization curve of water. It is also called vapor pressure curve. Now, what is our curve OC? OC. This curve is nothing but the melting curve of water of ice, or it is also called fusion curve. See, when you look at the transformation from water point, it is called fusion. When you look at the transformation from the ice point of view, it is called melting. Curve OC. Now, you have this curve OC. Fine. Give me a second. I'm just stopping these videos. Okay. So now, fine. So what is this curve? OC is the melting point curve. Is the melting point curve. And what is this curve? OA is the sublimation curve. At the melting point curve, what happens? You again take a pressure of 1 atmosphere. 1 atmosphere here. At 0 degrees Celsius, 1 atmosphere. 0 degrees Celsius, 1 atmosphere. You have two phases existing. Which are those phases? Ice, solid phase, water, liquid phase. Ice and water existing. Now, if you decrease the temperature further at the same temperature, at the same pressure, you have only one phase existing, ice. That means below 0 degrees Celsius, all the compound H2O will become ice. At above 0 degrees Celsius, all the compound will become water. So the water will exist between, this is also important. The use of phase diagram is to know between what range a given phase exists. So water will exist between 0 degrees Celsius and 100 degrees Celsius. Okay, fine. At the given pressure 1 atmosphere, this is important. At the same given pressure 1 atmosphere, water vapor will exist. At the same given pressure 1 atmosphere, water vapor will exist between 100 degrees Celsius to 374 degrees Celsius. After 374 degrees Celsius, you get a critical point, 374 degrees Celsius. After this, the compound water exists in a single phase where it is indistinguishable whether it is liquid or gas. Okay, so that phase is called critical point. That point is called critical point. Now, what is this curve? OA. It is called sublimation curve. You know what is sublimation? I told you it is the direct conversion of solid to gas, vapor. So you see the sublimation curve, very low temperature. Now at 100 degrees, at 0 degrees Celsius, if you take this curve, that the atmospheric pressure should be very low. Okay, it cannot be 1 atmosphere for an equilibrium to be set up between ice and water vapor. Okay, so this is OA, sublimation curve. Now we have a very interesting point called triple point. Triple point. What is this triple point? This triple point is a point in the phase diagram where all three phases are coexisting. That means at this point, you are going to find water vapor, as well as ice. That is fine. But that is not the actual use of phase diagram. The phase diagram gives you the value of pressure and value of temperature at which this triple point can happen. So what is the value you see? What is the value of triple point on the temperature axis? That is the x-axis, 0.0098 degrees Celsius. And the triple point's value on the pressure axis is much below 1 atmosphere. Okay, so that is what a triple point is. Fine. Now, like you have a curve AB for which there is one variable. At 1 atmosphere, you go on varying different temperatures. At 1 atmosphere, you can vary temperature to get water and water vapor. But for a point on a phase diagram, it is the value of pressure and temperature will be fixed. You can neither vary pressure, nor temperature. Both the values are fixed. Therefore, a triple point is called non-variant point, where there are no variables. It's a single value of 0.098 degrees Celsius and an atmosphere of 4.78 mm of Hg. A triple point will exist. And a pressure of 4.58 mm of Hg, triple point exists. If you increase the pressure slightly, this will vanish, triple point. Vanish means what? One of the phases will disappear. Only two phases will start existing. If you change the temperature a bit, again one phase will vanish out of three and only two phases will come into existence. Okay, so triple point is a non-variant point. Do you understand? Fine. So what is the metastable curve OA? This metastable curve OA is interesting curve. Why is it interesting? Because this is the curve, means you can, what happens to water if it comes to 0 degrees Celsius? It will start becoming ice. But it is still possible by careful manipulation of the condition. Below 0 degrees Celsius also liquid water can exist. Okay, interesting, right? Below 0 degrees Celsius also liquid water can exist. And that water is called super cooled water. This OA is the continuation of the water curve, water phase, even below 0 degrees Celsius. Where is our 0 degrees Celsius? Somewhere here, right? It is below 0 degrees Celsius, it is continuing. This is called supercooled water. And it can continue up to some point below 0 degrees Celsius. Further cooling will solidify it. But to hold supercooled water in that state, it requires very accurate maintenance of the condition of pressure and temperature. Okay, fine. So what are some characteristics of our phase diagram? Okay, fine. So in our phase diagram, the area AOC, what is the phase which is existing? Ice. And component in all phases is H2O. That is why this is called single component system, one component system. Area COB is water, liquid. Water means water liquid. Area below BOA is vapor. Now, for every area, always the number of component is 1 in this system and number of phases is 1. Because under every area, you see ice, water, water vapor. Number of phases is 1. Now, the application of Gibbs phase rule actually comes now. Without Gibbs phase rule also, you can construct phase diagram, no problem. But now, you apply phase rule to areas and find out how many degrees of freedom are there for every area. F is equal to C minus P plus 2. What is the value of C? 1, because it is monocomponent, water, H2O everywhere. Minus P, 1. Why is P 1? Because there is a single phase. We are considering area AOC. There is a single phase in it. So 1 minus 1 plus 2 is equal to 2. That means every area is bivariant. Okay. But every curve, I call it is univariant. Why? You again apply this. What is the curve's meaning? Along that curve, two phases exist. Is it not? You see this? Along OB, water and water vapor exist. Along CO, water and ice exist. Along OA, ice and water vapor exist. Therefore, for a given curve OB, vaporization curve, what are the phases in equilibrium? Liquid and vapor. Apply phase rule. F is equal to C minus 2. P will be 2. 2 plus 2. So you will get an answer as 1. So every curve is univariant. Area is bivariant. Triple point is non-variant. Why? In triple point, what is the number of phases? 3. Because ice, water vapor, liquid water, all 3 are coexisting. Therefore, for triple point, number of phases is equal to 3. So C is 1. 1 minus 3 plus 2. So you will get the answer as 0. Therefore, a point O is called invariant or non-variant point. Okay. So like this, we are going to summarize the number of phases and number of degrees of freedom. Number of components is fixed. It is 1. So how do the relationship between phases and degrees of freedom turn out? That is using phase rule you have to calculate. Okay. So this is the discussions we have made in this class. So what are the things we have learned? First of all, we have derived phase rule and we have constructed a phase diagram for water system and looked into the characteristics of water system phase diagram. Okay.